Great. Welcome to your first lecture. This lecture will focus on introducing Unit 0, some of the groundwork pieces before we begin our scientific journey. This lecture is specifically going to address the topics of scientific inquiry, which is like an updated version of the scientific method, as well as a brief intro to lab safety, although pretty much I'm going to leave that to your class syllabus, lab safety contract, and rules. So let's go ahead and begin. So first of all, usually in science, it is not a pretty package, okay? Normally in science, it's really just all about someone who's willing to observe and take notice of what's going on around them. So often what we say is that scientists will observe some type of phenomenon, some type of, one second, let me get my pen working. Some type of, if my pen would obey me, real world event / experience. All right. And sometimes though, it's more of a problem rather than some, wow, I can't believe the rainbow's here. Sometimes it's often, oh, wow, we have a really big issue. Like, why can't we stop this pipe from leaking? I currently have a broken washer at my home. A scientist might ask themselves, or someone who's thinking in a scientific way might say, I wonder why there's water all over my floor when I do a load of laundry and the door's not open. So what could be causing this? So oftentimes, according to the cycle of inquiry, scientific thinking starts with observing some type of real world event experience that you don't know how to explain yet. The key is that you don't know how it works, right? You don't know how it works yet, but you're curious about it, okay? Or some type of problem, right? You don't know how to fix it yet. And we often start by asking questions. That's one of the big things. Here it's all about asking questions. For you who are a little bit more literary humanities based thinkers, this might be the section that you call brainstorming, just putting everything on paper and being like, I wonder. And this leads us into the next process or step in the cycle of inquiry, is that scientists begin to figure out what they know and what they don't know by offering a preliminary explanation based on what they do know. So the what do we think stage is the stage where we often draw models. And models are useful because it helps us differentiate between what we know. One second. Again, my pen. I will get better at this, I promise, as time goes on. I'm just a little rough from the summer. Okay, it's kind of a combination of sometimes it's what we think we know, what we know. Okay, and what we consider possible. Maybe what we consider, oh, gee willikers. Consider what we consider, oh my gee willikers, what we consider to be a possible explanation. And so these initial explanations are super helpful, and these kind of go together, right? What we think is often depicted in a model, which is a kind of a written down version on paper of what's in our brain to paper, okay? And these initial explanations really try to focus on explaining oh, gee willikers, explaining the mechanism. We often want to get down to not just what we think is the cause or what we think is one thing that leads to another thing, but more the in-between of how does it work. This is we often are trying to figure out how it works. And for us chemists, we focus on how it works at the particulate level, at the particle level. If you're a physicist, you focus on it at the more nuanced force wave level, right? And this ultimately leads us to a question that we consider a testable question. Old school, hypothesis, right? What can we actually test with this? What type of investigation or experiment can I create from this? And so when we ask ourselves, how can we test it? We often create, right, some type of detailed procedure in which we carry out, right, a procedure that we carry out to answer the question, to answer our question from above, right? We, in the process of testing, okay, gather data. Our data can be categorized as quantitative or qualitative, right? The quantitative is the numerical, the numbers, and the qualitative is the descriptive. I really don't feel like I need to go over that one, okay? You'll be working a lot with that in your labs. And when we're looking at qualitative and quantitative data, we often try to look for relationships or connections between the data. Sometimes it's an if-then, a cause-effect. Sometimes we get a cause-effect, direct relationship or indirect. Either way, this, if I do this, then this will happen, right? The if-then. That could be a type of relationship, or sometimes we get in data a type of relationship where we just see more of a correlation, right? Well, there's an overlap, right? It varies. As chemists, we tend to deal with, at least in the classroom, a very structured nature. We tend to focus on the cause effect. That kind of is our focus here. This tends to be our focus in testing. We call the cause effect type of test where we're specifically looking for a if then, if I do this, then I get this happen. We call this an experimentation, and I chose the wrong color. Okay, an experimentation. That is a specific test looking for cause effect, is an experimentation. But sometimes we'll just delve into tests that are really just about gathering data. And if we're in a gathering data type of mode of investigation, where your whole point of your lab is just to get some constant, some value, right? There's no really connection with if I do one set of action, I'll get this result. We tend to call those kind of tests investigatory tests, investigations or investigatory tests. All right. We'll be dealing a little bit with both, but primarily focusing on the experimentation cause effect. All right. And then what we do is after we go through this process, of course, we summarize it in the what do we know? We go back to our original question and we use our data. Using our data, we answer or explain the question, the phenomenon, or the problem. Okay, phenomenon. And here's why it's important. When we do this, okay, this is where we get publicization or publishing of scientific work. So it's always important, one, that you go back and answer the original question, which was the whole purpose of the test, for one, closure, okay? But two, this is super important because this is where we grow and contribute to our scientific community. This leads us to publications and therefore contribution to the scientific community. So that's kind of the introduction to actually the bigger scope of understanding what science is about. We won't always be able to indulge in this level of inquiry, partly because of time. And in the end, like, the whole point of school is often to give you knowledge, not in discovering new things in terms of things that have never been discovered in the world, but to understand what has already been discovered so that you have an ability to launch from this place and go, hopefully some of you, into a world of discovering what has not yet been discovered. But we're still pretty much in this system and state of your education. You will be mainly looking into things that have already been discovered in order to understand them, as they are the groundwork for future scientific inquiry on your own at a much more advanced level. As far as lab safety, please just don't be silly in the room. Like, pardon my French, but don't be stupid in the classroom, right? If we're going to be working with fire, glassware, chemicals, right? The biggest priority is your safety. And so it is essential that you learn how to keep yourself and others in the classroom safe. So that is your first lecture. I really hope that you put me on 1.5 times speed, because I always start a little slow in these first lectures as I get back into the swing of things. But best of luck and see you guys soon.